We often think that the really big, profound laws of science are, well, out there, in far-off galaxies or hidden away in giant particle colliders. But what if I told you that some of the most fundamental laws of the entire universe are actually on display in something as simple, as everyday as a party balloon? Well, today, we're going to find out just that.
So really, what can a simple party balloon teach us about how the universe works? I mean, it's just a piece of rubber filled with air, right? Well, as we're about to see, the answer is a lot. We're talking about everything from the laws of motion that keep planets in their orbits, all the way to the invisible electrical forces that basically hold all matter together. All right, so here's the plan. We're going to look at just five simple things you can do with a balloon. But think of each one as a tiny little experiment. Each one pulls back the curtain on a really core concept in physics and material science. It just goes to show you absolutely do not need a fancy lab to see these incredible forces in action.
Okay, let's kick things off with the stuff we can actually see, the forces that create motion. We're talking about the bedrock laws of classical physics, the stuff Isaac Newton figured out centuries ago. And believe it or not, a balloon is the perfect tool to show us how they work.
So for our first one, we're going to look at something you can hear. It's called the screaming balloon. What you do is you pop a little hex nut inside a balloon, blow it up, and then spin it around really, really fast. And what you get is this shockingly loud, high-pitched wail. It's kind of startling the first time you hear it, but it's also a perfect demonstration of a really powerful force at play.
So what in the world is making that noise? Well, it all comes down to something called centrifugal force. See, as you're spinning that balloon, the hex nut inside just wants to fly off in a straight line. That's a property called inertia. But of course, the curved wall of the balloon gets in the way, constantly forcing it to change direction. That struggle, that resistance, creates what feels like an outward push, slamming the nut against the inside of the balloon. That's what causes the vibration and the scream. And hey, if you've ever been on one of those spinning carnival rides that pins you to the wall, yep, that's the exact same force you're feeling.
All right, let's move on to our second demonstration. This one's a total classic, and for good reason, the balloon rocket. You've probably seen this before. You tape an inflated balloon to a straw, you run a string through the straw, and then you just let it go. And whoosh! The balloon zips forward along the string with a surprising amount of speed.
So what's the science here? Well, it's actually one of the most beautiful, elegant, and important laws in all of physics, Newton's third law of motion. It's a really simple idea, but it has these huge implications. And honestly, the balloon rocket is one of the best, clearest examples of it you'll ever see. It really is a simple trade-off. You've got the action, all that air getting forced backward out of the balloon's opening. And then you have the reaction, the body of the balloon getting thrust forward along the string. For every action, an equal and opposite reaction. It's really that simple. And the craziest part, every single rocket, from this little balloon to the massive behemoths that launch satellites into orbit, they all work on this exact same fundamental principle.
So, we've talked about the forces of motion, things we can see and feel pretty easily. But what about the forces we can't see? Our next couple of experiments are going to dive into a world that's totally invisible, but just as powerful, the world of electricity.
Okay, for this one, all you need to do is rub a balloon on your hair, give it a really good rub, and then hold it just above some tiny little pieces of paper. And then something that honestly looks like pure magic happens. The little bits of paper just leap up off the table and stick to the balloon, like they're defying gravity, and you're not even touching them.
Now, of course, it's not actually magic. What you're seeing is static electricity. That friction, the rubbing of the balloon against your hair, it's literally moving tiny subatomic particles around. This creates an imbalance of electrical charge, and that imbalance can create a surprisingly powerful force of attraction.
So here's the breakdown of what's really going on. When you rub the balloon on your hair, you're scraping off these teeny, negatively charged particles called electrons. They jump from your hair onto the balloon. So now the balloon has this extra negative charge. The paper on the table, it's neutral. But when you bring that negatively charged balloon close, it actually pushes the negative charges in the paper away and pulls the positive charges closer. And that little bit of attraction is all it takes. It's strong enough to overcome gravity and lift that paper right off the table. Okay, so up to this point, we've been looking at forces outside the balloon, or forces the balloon creates. But for our last two examples, we're going to shift our focus and look inside. We're going to explore the amazing properties of the rubber material that the balloon itself is made of. Now, here's one that just feels wrong. We all know what happens when a sharp object meets a balloon, right? Pop. But what if I told you that you can actually push a sharp wooden skewer all the way through an inflated balloon without it bursting?
So how is this possible? Well, there's a little secret, a bit of prep work. All you do is put a piece of clear tape on the balloon first, maybe in an X shape. Then you can carefully, slowly push the skewer right through the middle of the tape. And the result? You've got a skewer going straight through a balloon that's still perfectly inflated. And this trick is a fantastic illustration of something called polymer elasticity. See, the rubber of a balloon isn't a solid sheet. It's made of these super long, tangled up chains of molecules, kind of like a bowl of spaghetti. When you poke a tiny hole, all that air pressure inside wants to rip that hole wide open in an instant. But the tape gives it some support, and more importantly, the balloon's own stretchy polymer chains are able to move and press in around the skewer, forming a nice tight seal. It prevents that massive catastrophic tear that we all know as the pop.
All right, let's take that idea one step further for our final and maybe most mind-bending demonstration. What happens if you fill a balloon with water and then stick a bunch of sharp pins right through it? You'd expect a sprinkler, right? But no, the water doesn't spray out at all. It just stays inside.
This is that same polymer elasticity we just talked about, but taken to the extreme. Just like with the skewer, those long, flexible rubber molecules squeeze in and form a perfect, watertight seal around every single pin. Think about that. That seal is strong enough to fight against the pressure of all that water trying to get out. It's an incredible, visible showcase of the forces happening at a molecular level right inside the material itself.
So, after all that, after screaming balloons and rockets and levitating paper and things that should have popped but didn't, what's the big picture here? What have we really learned from all these simple tricks?
Well, the most important takeaway is this. These aren't just cool party tricks. They are real, physical demonstrations of universal laws. The very same force that keeps planets circling the sun, that's what's making the hex nut scream. The exact principle that launches massive rockets into space, that's what's pushing our little balloon rocket along. This balloon stops being just a toy, and it becomes a window into the fundamental physics of our universe. You know, it reminds me of something Albert Einstein once said. The most beautiful thing we can experience is the mysterious. And that's what these little experiments let us do. They let us touch that mystery. They let us take something completely ordinary and peel back the surface to find the elegant, profound, and powerful laws of science that were hiding there all along.
And that really leaves us with one final big question to think about. We've just seen how a simple balloon can act like a lens, letting us see these huge ideas from physics, electricity, and material science. So, if these fundamental laws are so clearly visible right here, in this one simple object, just imagine what other incredible scientific secrets are hiding in plain sight all around you right now, just waiting for you to get curious.